Hello everybody, this is Christine. Welcome to the second part of electrobiology, myth and magic. Now today we are going to do a more of a deep dive into the shapes of nature. Now this one is going to be more technical, so don't be ashamed if you need a pillow and you just need to sleep on it, drool on it. I know I have many days of just staring at fruit and reading boring material. So anyway, sometimes things are just boring to absorb. So anyway, and also I don't have anything against quantum or relativity. I just don't understand some of those concepts, and I definitely am not a theoretical mathematician. So the math that is in this video is just going to be pretty much everyday geometry. So anyway, with all that being said, sit back, relax, take your troubles to the door, and maybe grab a pillow too, and join me with some alternative biology theory. All right, let's go and see you on the other side. Let's jump in with both feet. So the last video we discussed from what I believe, or where I start my understanding of this whole process anyway, is the inertia of the electrons, and that inertia where right before it needs to rebound and come back into the center. So that is going to set up the limits of your field. So, and then we discuss the in and out, or the rebound, and the cycles, which is the frequency, which can be labeled and measured in something called hertz. And that, let me get to the right page here, that is going to influence, that motion of inertia is going to influence molecular structures and eventually tissues. So, and then we discussed the paths of inertia. So basically from the center, it's going to lose inertia, get to a pole area, and then it's going to come in and gain its inertia. So whenever you come in, it's going to be a gain, and whenever you push out, it's going to be loss, up until it can't go any further and needs to rebound, and then it's going to gain. And we just discussed that with an egg model here. I'm sorry that these are all wet, but I did freeze them because I just didn't want to keep on using fresh eggs. So they are cracked too. I don't know if you can see that, but anyway. So this is just a good model of that figure 8 motion here. So here is your center, or the line of inertia, the most active part and the easiest to break, and then you have your two dipoles, which if you either do in molecules or whatever it is, it's going to be a charge differential on each side. So with that being said, this was a stylized magnet. Now let's see if I can do a close-up of that. So if you deem either pole, doesn't matter, north or south, you can get more into it with red and blue shifts, but we won't do that now. I should have did that in the other video, but I didn't. But anyway, so these are the points of gaining and losing inertia. So you're going to see this figure 8 here. And then this is going to be your line of inertia. This whole thing, in reality, is that. So this whole complex is going to be called a toroidal field. It's just a round field, that's all. So if you were talking about regular magnets here, you can actually see this happening in nature as well. Before I get to the toroidal field, because I know I forgot this part in the last video. So you can actually see that in some plant structures here. Now, I don't know if you can see that. I'm hoping that you can. So this is going to be your poles, so either north or south. This is going to be the rest of the toroidal field here, the rest of your inertial lines, and then this in the center is going to be your line of inertia. Okay, now instead of a flat surface, let's do a rounded surface. So this tomato here would be considered a toroidal field. So the skin is the limits of the inertia for this fruit. So if you think about it, the raised areas are the areas of gaining inertia, and the V in the middle is the declining or the waning inertia that's not collapsing, but converging upon itself. So, and then I sliced open an orange, and you're going to be able to see the same thing. So, in the shell here, this is going to be the, I'm not sure if you can see that, that is going to be the gaining inertia. And then the inside, or the orange slice, is going to be the decreasing or the convergence of decreasing inertia. And you can actually see that in the actual orange slice. This is just basically the negative of the shell here. So, say if these lines are the gaining inertia, and then this slice in the middle, this is going to converge, and this is the decreasing inertia. Did you guys grab your pillows? Because my cat's already sleeping. So anyway, no video like this is going to be complete without the Fibonacci sequence. So here we go. And so what is that? It's basically a fractal pattern. So it can either increase or decrease. So let's just start at the beginning. So you just start with a point, any point, and then you just add to it. So now you add these 2 points, which are the fractal, and you come up with the whole. So then we're just going to go down the sequence. So we're going to take this whole section plus one of these sections. So in this case, it's going to be 2 plus 1. 2 plus 1 equals 3. So, and then it just keeps on going from there. So 3 plus 2 is what this represents. It's going to equal 5. So, and then it's just going to go on and on and on. And subsequently, it's going to be the same scaling up. So if we took the next one, so the next line is 8 here. So if we did a 3 minus 5, and we're just going to be left with 5. So basically, you're just going to lob off the last section that you did. So basically, if we were going to go backwards up to 0, we would lob off 2, and then we would just get 3. So I don't know if you can see that pattern that's happening there. So like this one, we would just lob off 1 and we get 2, and so on. So lots of people, they don't express it as lines. Usually they're expressed as boxes. So everybody's familiar with that nautilus shape. So basically we'll start out with the 2 plus 1, so you have that 1, so 2 plus 1, that's going to be a whole section, and that's going to equal 3. Now you're going to take this all together, that's going to equal 5. We're going to take all this together, and it's going to equal 8, and it's going to just keep on growing and growing and growing and growing. And that's how you get that nautilus pattern. So I already have it in orange, but I don't know if you guys can see that. So you get that kind of swirly pattern going on. Okay, so now that we have the Fibonacci sequence, so now what does that mean other than increasing and decreasing patterns and fractals? So basically what it is between any one of these sections. So if you were to divide one into the other, so say in this sequence, in this section, it will be 13 divided by 8. You'll get a ratio of 1.62. So there is a ratio of 1.62 between these. And then as you go up the scale, I actually just skipped one because I had room issues here. But basically, so if I was to do 8 divided by 5, that would be 1.6. So the ratio between these two is 1.6. Now you can see I just did up to 3 divided by 2, but there's a funny phenomenon that happens. So mostly, because that's 1.5. So mostly, if it's greater than 2 and you keep on going down the sequence, it's going to level out and it's going to get closer and closer and closer to the value of 1.618. And that is the golden ratio. It is just the ratio between two segments. So it's going to be the ratio between this and this little added point right there. That's just the ratio between two of these sequences. Okay, so how do we apply this to inertia? So if we just start off with one line, and then we'll go 1.6, so we're going to go around and end up here. Now if we do another, if we take 1.6 from here, then that's how we get this. So we're going to go 1, and this is going to be your half, and 0.6. So what's going to happen is, when you're talking about inertia, it's going to have an equal push and pull between all of these angles. So now what can we do with this arranged inertia? Well, there's a few things. We can stack them, we can add them, we can put them next to each other. So let's just start with stacking. So now we have the 3-point star. We have 1, 2, 3. Can be arranged in different shapes. So I just drew just the outline of this. And also I think it's kind of funny, if any of you guys are Star Trek fans, that's actually their symbol, and I think they have like a little star in the middle. But anyway, let's move on. So anyway, and then you could just go ahead and draw a triangle. Now there's a lot of cultural and spiritual meanings to this, so, and it's the point of different trilogies in different cultures. So if you're a religious person, maybe you would consider it Father, Son, Holy Ghost. If you didn't, maybe it would be thought, action, result, that kind of thing. So anyway, this is a 3-pointed star. So if we were going to stack, it's going to stack in the way that gives it the most push and pull. So basically it's going to be equal and opposite. So basically, instead of this having the point going down, the point is going to go up. This one's going to be the Y shape. Here's another representation just like that, equal and opposite. And also we're going to have an inverted triangle. Now, in a lot of cultures, this triangle up here is going to represent the male, and this upside down triangle, because of the V, so the staff and the V, so this is going to be, you know what, and then this is going to be the V of the female. So when we stack them together, they're going to make a 6-pointed star. And then I'm going to spare you the details because I'm not a good artist. So, and then the two triangles are going to join, and it's going to be this arrangement, the 6-pointed star. So in a lot of ways, it's going to be the joining of the male and female, and then any cultural significance that you would like for the trilogy. But basically what it's going to be is the opposites of the same entity. So where did we see that before? Well, we saw that right at the beginning. So if that's polar opposites, it's going to be a part of the same entity. So I just thought that was a nice throwback to what's going on here. Okay, so let's just do one more stack. So we have the 3, 6. We're going to stack one more to a 9-pointed star. So we have the Y, we have the upside down Y, and now we're going to stack a third one coming in from the side. I apologize, I kind of messed up there. But as you can see, once we stack them, they're going to be a 9-pointed star. Okay, just keep that one in mind. And I know these don't look the same as that, but I just couldn't do it with pencil. So anyway, you can also put these right next to each other. So when you have the addition, and then they're going to close the gap here, you're going from the points, you're going to have a 9-pointed star and 2 centers. The 9 plus 2 arrangement in this complex. So where do we see that? We see that in flagella. So what's the point of, like, say, bacteria and anything that has like a big tail for motorization and getting around? Well, that just means that there's big time power distribution, I should say, coming out of this complex. So let's add this inertia. So we have the 3-point star. So we have the 1, 2, 3. Now if you are going to follow the Fibonacci sequence, so that's going to be 3 plus 2. So all the way back here. So we have the 3 plus 2 equals 5. So the 3 plus 2 equals 5. So we're going to do 1, 2, 3, 4, and 5. Now 5-point stars are kind of interesting in the way that they can follow the pattern, or they can do the flip-flop, and they can choose to stack if they'd like. So 5-point stars can either turn into a 6-point star following stacking, or it can continue on with a Fibonacci sequence. So if it was going to add, it's going to do this. It's going to do 1, 2, 3, 4, 5, 6, 7, 8. So that's going to turn into a 8-point star. So like I said, 5-point stars can turn either into, it's going to add that extra tail, it could either become a 6-point star, or it can follow the sequence and it can be an 8-point star. So with that being said, now it's going to turn into a square or a diamond pattern. And sometimes they can, the plants or whatever the organism is, can actually break these up into sequences like that. So if you are a plant and you are using this set of arranged inertia, you would be maximizing the amount of surface area for the production of power in the leaves. Now, say if you needed that to be transferred into a flowering body, it could be transferred usually into a 5 or a 6-point star. But either way, the plant is going to lessen the distribution and concentrate more energy in seed production. Okay, let's go back to 3-point stars. I gotta do this real quick because it's this celery is needed for dinner. So basically, you're going to have 3 big structures coming out. So it's 1, 2, 3. Now we're gonna stack that, and we're gonna do a 6-pointed star. So remember, here's like 1, 2, and 3. So you have points that are associated with it. Now we're going to go in the middle, as you can see that. So that's going to be 1, 2, 3, 4, 5, and 6. This is a slice of cucumber that I took from earlier. So as you can see here, we're going to have that same 3 patterns. So 1, 2, and 3. but as you can see where the seed production is, 4, 5, and 6. And in some slices you can actually see these coming out from the center. And I'm not sure if this piece you can actually see that. Now I just have an example of the 5-pointed star. Now it's a little bit difficult to see. So you have your 3-pointed star. So 1, 2, and 3. You're going to have outcrops of 4 and 5, 6, 7, 8. So let's scale this up way up to planetary systems. This is the hexagon of Saturn. This is at one of the poles, and basically just how we were talking about, this is going to be a 6-pointed star. So here we go, 1, 2, 3, 4, 5, 6, and a center. So you're going to get that shape with that layering, and so there you go. That is like the outside shape, just like the triangles here. And then we are going to jump into Jupiter. Okay, that is Jupiter at the South Pole. So what do we have here? We have 5 points. Now these are big cyclone systems, but it's going to be the same as your points or a 5-pointed star. Here we go, 1, 2, 3, 4, 5, and a center. Now let's go up to the North Pole. Okay, here we have an 8-point system here. So remember the Fibonacci sequence where we were going to from 5 to 8, we're just adding 3 more. So here we go, 1, 2, 3, 4, 5, 6, 7, 8, and one big cyclone in the middle. So you see, it really doesn't matter if you're a fruit like an apple with a 5-point system or a planet with an 8-point star. It doesn't matter. You're still gonna apply the same results of the push, pull, attract, repel, all that. And I know that they can run experiments with magnets and stuff, but basically it's all the same thing. Okay, so let's put all these concepts together. So it could be any seed, but I'm choosing an apple seed here. So seeds are polar. So the Earth's surface is going to be negative. The ionosphere is going to be positive. Now it doesn't always have to be the case in large storm systems. This can actually reverse, but in general, this is going to be true. So anyway, let's go back into the seed. So now here's going to be a duality. We're going to be splitting the heaven and the earth, and whatever is going to happen, so from what happens from above, so below. So there's going to be lots and lots of things that are happening underneath the surface, but we're just going to concentrate what happens above the earth. So for now, so anyway, it is going to start at the earth. So anyway, the seed is going to send a runner up, and the runner is going to be negative because the ionosphere that is positive is going to almost suck that plant right out of the ground. So the negative is coming up, trying to meet the positive. It's going to start growing until it starts and it hits a terminus. At the terminus, it does have a receptor. So now that the inertia can't go anymore, it is actually going to split itself to allow it to have more inertia to grow. So, and then this branch, if you will, hits a terminus, and it's going to do it again and again and again and again and again. Okay, so the Fibonacci sequence does play a little bit of a role. It doesn't have to be perfect. So remember how we were saying that it goes from long to shorter to shorter to shorter, or shorter to longer to longer to longer. Exactly the same thing. So basically each section is going to express the ratio of 1.6 smaller than this. This is going to be 1.6 smaller than this, and this is going to be smaller than that. All right, so there you go. There is that growth of the tree. So you don't have to just apply that to trees and plants and things, but you can also associate it with the growth of blood vessels, but also blood vessels are in a closed system, so we can go over that later if you wish. But anyway, and also this is kind of cool because if you turn this around, it is also the pattern of lightning. So lightning will come down. So now this is the atmosphere. This is the stream coming down. And you'll see if it doesn't hit the ground, this is the pattern that it's going to take. But the earth, since it's going to be negative, so it's going to send almost the opposite of the plant. So it's going to send a lead up. So now if these structures of the lightning, if it meets, now the lightning can complete its circuit. Now there's other things happening up in the atmosphere like sprites and things like that, so we won't get into that. But anyway, that would be the structure of a lightning bolt. So now I have drawn my makeshift apple. So I'm gonna switch over to a real apple that I chopped up. So here we go. So let me explain this a little bit. It's basically going to be a recap. So this is the field or the outer limitations of the inertia for this apple. So this is going to be the poles here, and this is probably going to be the negative pole, because the ionosphere is positive, and this is probably going to be the positive because the earth is negative. Okay, so now that we have the poles, I'm just going to, it doesn't really matter, but it's easier for me anyway. So anyway, here is the poles, here is the limitation of inertia, so this is the field of the apple. This is the plane of inertia, remember that figure 8 pattern. And this is going to be the area of the most activity. So, all right. So I've got another cut apple here. Here is the one with the lovely 5-pointed star. So as the inertia is coming in, it's going to gain inertia. And then when it comes out from the top, it's going to lose inertia. So as this is going on, this is going to have the, excuse that seed there, I'm just going to pop them right back in. So this apple has chosen a 5-point star for the most effective seed production and the seed distribution. So what does that mean? So that means that the inertia is going to align itself up as these star patterns, so it's going to have the most efficient energy use to develop these seeds. So, and then remember what we were saying in the first video. So if an apple, because of the shape of the apple, if the apple should drop, it's going to be okay because of this round shape here. The round shape is very strong. But if you take it here and it drops on its side, it's most likely going to break or rot or do anything like that. And it's going to distribute the seed right underneath the tree, and it's going to have too much competition for the parent tree. So if it drops this way, most likely it's not going to damage the fruit too much. So either us, other animals, they can eat it and redistribute the seeds. So anyway, that is it for this video. I do apologize that I'm not going to go too much further in it because there's just too much information. But I promise you, I will get to the magic wand in my daughter's Halloween costume. But I think in the next video, I am going to cover the overlap of fields and this beautiful pattern from the Fibonacci sequence. Okay, so if you're interested, please join me the next time. I hope you guys are all doing well. Stay magical, everyone, and we'll see you the next time. Bye-bye.